Hello, welcome back to physics. I am going to be going over week 3 FRQs 1 through 4. I want to tell you that FRQ 1 and 4 are that paragraph writing, so make sure when you justify your answer and you're looking at that paragraph that you actually look at the student exemplar. I'm going to give you some pointers here on how to do that. But I will link that in the video below. I'm like one of those YouTubers. Subscribe below. Not actually. So look at the student exemplar. I'm going to give you some pointers right now, though. Here we go. Number 1. Make sure you have your work in front of you. Make sure you also have the actual FRQs, just like on test day. You will have your work either on paper or be typing it, and then you'll retrieve the answers from the beautiful internet. So here we go. We have 3 balls, case A, B, and C. One is launched initially like so. One is at an angle. And one is at an angle downwards. We know that this component here is 5 units. This is -1 units. This component is 5 units. This component is 1. I'm just getting these from the graph. This component here is 5 units, and there's no vertical components for that there. Part A, it says, in which case will the balls travel the greatest horizontal distance after 2 seconds? So I only care about horizontal. So A, I see horizontal components, there are 5 units here. B, there are 5 units, and C, there are 5 units. So in projectile motion, remember horizontal and vertical are separated. We don't put them together. Usually we break them into their components. So this vector component is 5, 5, and 5 in the horizontal direction. Because of that, and because there are no external forces in the x direction to make it either speed up or slow down, that means the horizontal component of this is always going to be 5. So the greatest horizontal distance, if this is going 5 meters per second, 5 meters per second, 5 meters per second, they're going to all go the same horizontal distance. I want you, when you write that out in your paragraph, I want you, as you saw in the slides, to use the A, B, C, D. So that's A, answer it. All the same. B stands for basic physics. What is the physics of this? You can say something about your X and Y components. All have the same 5 units in the horizontal direction. So there are no external forces. Horizontal forces. Cite your data. You could say that 5 units, some type of number. Got that from the problem. And then draw it all together. What's your conclusion? Therefore, they're going to all go the same. So restate that with your wording there. That's all you got to do for part A. Part B, though, asks you about, what does it ask you? Has the greatest velocity before striking the ground. So sometime later, they're going to follow projectile motion. So they're all launched off a building. And they're all going to follow the path of projectile motion. So like this. This one, though, was launched straight out. This one was up. So it's going to go up a little and then go down. This one is going to just go straight down like this. And you want to know what the velocity before striking the ground. So let's say here, right before striking the ground, we have our velocity vector like so. These are not drawn to scale. These are not. So we know the horizontal component is not going to change. This is going to be 5. This is going to be 5. This is going to be 5. Not changing. But the vertical components are all a little bit different. This one started at 0, 1, and -1. So to find, we're going to call this velocity final in the y direction. Velocity final in the y direction. Again, velocity final in the y direction. If you know these 2 components, then you can find this component here. It's just asking you to justify what your answer is. So you don't have to, on the AP test, you won't have to do calculations. You won't have to draw anything. You just need to do, again, the ABCs, answer, basic physics, cite your answer, and then draw it all together. Again, that student exemplar is going to be linked on Schoology. In order to find this final velocity component, I'm going to use the equation velocity final squared is equal to velocity initial squared plus 2 times acceleration times distance. Be careful on this. The distance here, some of you were asking, is x minus x initial. X initial, they all start off at the exact same point, right? And they all fall down a certain distance because they all fall off the same building. So this distance they fall, the initial distance, is the same for all of them. The distance they fall down is also going to be the same for all of them. So if you started watching those AP Physics videos, if these are the same for all of them, you can just put a 1 there. Acceleration we know is 9.8 on Earth. Initial velocity, and remember this is only in the y direction because we're trying to find this final velocity here. This case A is 0. This case is 1. This case is negative 1. I want you to think about what is 1 squared? 1. But what about negative 1 squared? That is also 1. Therefore, these two, A is going to have the smallest velocity, and then B and C will have the largest velocities because they will have a larger component right here, larger final velocity component. So check out that student exemplar. Message me if you have more questions or you want me to explain this better, but I'm going to move on to number 2 right now, which looks a little intimidating at number 2, but do not get intimidated right off the bat. It's a lot of fun algebra, I'll tell you that. Cool. Like my new handy dandy wristband. Okay, number 2. You have 2 blocks and you have this system. You need to draw forces acting on the blocks. So they might not grade you on this. On the AP test, they say you don't need to draw any diagrams. They might give you the diagrams. You might have to draw. You definitely need the components of the diagram, though, to do part C, D, and E. So it might not be graded. However, you might have to do it as part of setting up your problem kind of thing. So that's why we're practicing it. Number 2, part A. We have mass 1 first. And we have mass 2 over here. It's part B. All right, both of them are on Earth, so they experience the force due to gravity. You can draw them as blocks if you printed them off, so you can also draw them as dots. Totally up to you. Both are accepted. Remember, you need to label your forces. What is this? Is this force of gravity, force normal, force little g? This guy here is on Earth as well, force of gravity. We read in the problem that this is on a rough surface. So rough, I'm thinking already friction. So there must be a force of friction that acts in the opposite direction of the motion. I know that the object is going to start moving that way because there is a force of tension is connected by a rope. If I left it just like this, this would say these forces are balanced, cool, it's not moving, but we have a force that's pulling it straight down. So that means it's accelerating down into the ground. That is not true. It's sitting on a table, so we have an equal and opposite force. If 2 surfaces are in contact, we call that the normal force. Force normal. Like so. That's all you need. Quick point here, make sure your arrows touch the object. And that they are labeled. So little f is friction, tension, normal, gravity. You totally can label them as just capital T for tension if you want, but just be very careful with your variables when you start doing some algebra with this problem. I like to keep it as a capital F so I know it's a force. Here, again, if this was the only force, it would be accelerating straight down. We know that is not the case though. Something is pulling it up. And that is the string, force of tension. Do I need to draw a normal force here? No is your answer because it is not touching anything. Remember, normal forces are only if objects are in contact. So like this. Cool, that's part A and B. Now you need to find the minimum value of the coefficient of static friction that will prevent the block from moving. Oh, that's a lot of scary words. In terms of M1 and M2. Do not panic. This is easier than it looks. I'm going to keep my lovely diagrams here because I'm going to need them to do this problem. So essentially that's telling me what is the coefficient of friction, of static friction. That means it's not moving. I need to find that. That's what I'm looking for. So immediately, I'm thinking to myself, I have the force of friction here. I know that has to do with the coefficient of friction. If the force of friction and the force of tension were equal, or the force of friction were greater than the force of tension, then it wouldn't move. So I'm going to use that idea and set these equal to each other, essentially. So let's write some equations out. So it is not moving. Essentially, that means all my net forces should equal 0. So let's start with this picture here. Let's do the net force in the y direction is equal to 0, because that means it's not moving, it's not accelerating up or down. So I know I have a force normal in the positive direction, and in the negative direction I have force of gravity. Cool. What about in the x direction? F net in the x direction is also equal to 0. So they want to know what's the coefficient of friction, static friction, to keep it on the table. So we'll set this equal to 0. We have force of tension, we'll say is our positive force, is equal to force of, nope, not equal, minus the force of friction. We'll say that's negative, this is positive direction. Don't have coefficient of friction in there yet. However, I know from my equation sheet the coefficient of friction is equal to the force of friction divided by force normal. Ooh, is that going to help me? Yes. Sorry, did a lot of math here. Cool, I see force of friction is here, so I can substitute static friction is equal to the force normal. Ooh, it's all over the place today. Force normal is equal to force of friction. Awesome, sweet. What about the force normal here? I wrote this equation. Force normal is minus force of gravity is equal to 0. If I pull this to the other side, I get Fg is equal to F normal. Some of you maybe already plugged that in, totally fine. This is just where you get that. Fg is also mass times gravity. So here, I can plug in, run out of room, force normal, M. Remember to keep these consistent, we're just talking about the first box, and then we'll go to the second box. Oh, sweet, we already have coefficient of static friction, that's what we're trying to solve. In terms of mass 1, we'll incorporate mass 2 in just a second. So we're already halfway there. Sweet. Let's keep building on this equation. I'm going to pull this to the other side. Now I have force of friction is equal to force of tension. Force of friction I have right here. A lot of substituting. Coefficient of static friction, mass 1 times gravity. Boom. Now we need to incorporate mass 2 in there somehow. I see the force of tension here is going to be the same as the force of tension here. Why is that? Because it's acting on both objects. So just like if you're pulling a string, it's not going to be tighter in one area than it is at the other. The force of tension in the rope, it should be uniform. So if we solve for force of tension here, with some algebra, we can set these equal to each other. So let's do that. Again, this guy is not moving. There are only forces in the y direction. So I'm going to say F net y is equal to 0, which is also equal to force of tension minus force of gravity. Pull this to the other side. Force of tension is equal to force of gravity. But the force of gravity acting on this is mass 2 times gravity, mg. So now I have force of tension. I'm going to set these equal to each other. Coefficient of friction is m1 times g, which is equal to m2 times g. If you have the same variable on each side, they can cancel. Again, I'm solving for coefficient of static friction, and I get m2 over m1. Just like that. Cool. Pause that, rewrite that, re-listen to it, text me, call me if you need to do that again together. Cool. Should have done this smaller. All right. The blocks then are set into motion by a momentary downward push. You need to solve for, in terms of m1, m2, and gravity, derive an equation for each of the following. What is mk? That shouldn't be coefficient of friction. Sorry. Kinetic friction. Anyways, here's the acceleration of m1. Cool. So I want you to know, though, the acceleration of the system is going to be the acceleration of 1, which is also the acceleration of block 2. If this block starts moving, it's going to accelerate at the same rate as this block. It's not like that this block starts accelerating down and then this one just goes super slow and then it eventually catches up. Because the tension is the same in both, their acceleration are the same. So if you find the acceleration of the system, or 1 or 2, it should be equal. Cool. Awesome. So again, we have F net is our net force, is equal to the force of tension minus the force of friction. Remember, this is a positive and this is a negative direction. This time, though, this is not equal to 0. We know Newton's second law says F net, mass times the acceleration, is equal to force of tension minus force of friction. We already have an equation for force of friction, or that we can incorporate force of friction into. We now have kinetic friction, coefficient of kinetic friction is equal to the force of friction divided by force normal. Again, it's not moving up or down, it's only moving sideways, so the force of gravity is equal to force normal. So we can plug that in here. Force of gravity is mg, which is mass times g. We're going to rearrange this to equal coefficient of kinetic friction. Awesome, then I'm going to plug it in for this. Now I have mass 1, acceleration is equal to force tension minus coefficient of kinetic friction, and 1 times g. Awesome. What are we trying to solve for again? Acceleration, your acceleration of the system. How fast is it moving? Is it gaining speed because of that external push? The reason I'm doing this is because, again, I know tension is going to cancel out and I can incorporate both of these together, and I know I have to incorporate m1 and m2 into my equation. Let's pull this to the other side. Cool, there's our equation for force of tension on the left-hand side. Beautiful, let's solve for force of tension here. So now we have F net is equal to force of tension minus force of gravity. Again, this is not equal to 0 in this part. Part C it was, part D it is not. So we have Newton's second law, mass times acceleration is equal to the force of tension minus mg. Cool, let's get force of tension by itself. Right here, there needs to be one more thing. I want you to see that this block is moving in this direction, so it's moving in the positive acceleration. This block, however, is accelerating downwards. So yes, it's experiencing tension, force of gravity, but the acceleration for this is going to be negative. This is not minus, this is just times -1, because your acceleration is negative in this case. Cool. We're going to set these forces of tension together, set them equal to each other, and solve for A. It's going to get a little bit ugly with our algebra, so I'm going to erase some things and then keep working over here. Awesome. So force of tension, set them equal to each other. So I have M1A plus coefficient of kinetic friction. M1G is equal to negative M2A plus M2G. Okay, again, we're solving for acceleration, so I want to put all the like terms together. So now I have M1A plus M2A, and put all the G's on the other side, is equal to M2G minus coefficient of friction, M1G. These are different masses. You can't cancel them. You can't add them together. Be careful. The G's, though, we can factor out, and the A's we can factor out. So now we have A M1 plus M2 is equal to G times M2 minus coefficient of friction. Beautiful. Getting somewhere. All right, now I need A by itself. Remember, this is one whole term, so I can divide both sides by that to get rid of it, and you get acceleration of your system, which is the same for M1 and 2 acceleration. It's equal to G M2 minus coefficient. There you go. There's your answer. All right, remember this is a little bit uglier, but you will get half the points if you get to this step, if you just solve for the tensions. If you don't get to this very final step, that is totally fine. Make sure you get as far as you can and try it and attempt it. It's my biggest piece of advice. Now I need to solve for tension. So I'm going to leave that there. All right. Part D. E. Really good at my lettering today. You need to solve for the force of tension. You found in previous part, you found acceleration already. You have equations that say what tension are, so you can use M1 or M2. Both of them will have the respective variable in the answer. So I'm going to use our equation force of tension is equal to M2G minus M2A. Then I'm going to plug this beautiful thing in here for A. If you write this and then you plug this in, that's all you need to do. You don't need to simplify. However, it is simplified on the answer key if you want to check that out. So A is G M2 minus. Cool. There's your answer. Solve for the force of tension. Remember, you're not looking for any numbers. You just want it like that. Cool. All right, let's jump to number 3. This time you're on an elevator. If any of you live in an apartment building and have a scale at your house, you can actually do this exact problem and see how your mass doesn't change, your weight changes as you move up and down on an elevator. Cool. FRQ number 3. So you're at rest. The scale says, because you read in newtons, not in pounds, that you weigh 840 newtons. That is your weight. That is also mass times gravity. Then you begin to start accelerating upwards for 2 seconds. Then you move at a constant speed for 10 seconds. And then the elevator starts to slow down. So when you're slowing down, you are not going physically down. You are just decelerating. So your speed is decreasing, and eventually you come to rest. So part A, again, it asks you for a beautiful paragraph. Explain why the weight, why that reading on the scale is changing, why it increased and then decreased, increased at the beginning of the motion. So you needed to say something. You can, again, look at the student exemplar, but you needed to say something that there was a change in the net force. Why did this happen? Newton's second law says F equals ma. The elevator was accelerating. So F net, when you're standing, two surfaces are touching, is your force of gravity is pulling you down, but the elevator is pushing you back up. So that is going to be the force normal. Because Newton's second law, F equals ma, this here is your mass times your acceleration. If you have a positive acceleration, if you increase this side, you must increase the other side of your equation here. Gravity is never going to change unless you go to another planet. So that's not going to change. So the only part of your equation that you can change is your force normal here, which is the force of the scale pushing back up on you. So your mass, let's say, is, I don't know, you can figure it out, 84 kilograms. Acceleration, that's how fast you're going upwards. So again, the normal force is the thing that's changing. Cool? Cool. Awesome. Part B, you need to draw some diagrams. So again, you're not drawing diagrams on the AP test, but you might need them for your explanation later. So make sure you know how to draw them as well. So here, first situation, second situation, and third situation. Let's start with the second one. Let's start with the force of gravity. Force of gravity is never going to change. These arrows should all be the same. You're on Earth, it's always going to be mg. Your mass doesn't change unless you eat too many cookies, and g will always be 9.8 unless you go to another planet. So those are always the same. Here in the middle, you're moving at a constant velocity. So that means your acceleration is equal to 0. That means your net force is also equal to 0. So that means this force has to be equal and opposite to your other force. So these arrows are equal and opposite. Cool story. All right, this one, your acceleration is positive. This one, you're decelerating, so your acceleration is negative. So your net force here is going to be negative. Your net force here is going to be positive. So that means you need more forces acting upwards than there are downwards. So that means your arrow has to be bigger. You just need to make sure it's bigger than force of gravity. It doesn't have to be exactly proportioned out. Cool. This one, your arrow needs your force normal. The two surfaces are still in contact, but your normal force is going to be smaller. That means if you add these together, your acceleration is going to be negative. It told us it was decelerating, and it was slowing down. The elevator is coming to a stop, so acceleration here is negative. All right, let's draw some graphs. See. Okay, again, you will not have to be able to draw these on the AP test, but you might be given them and you have to describe what they mean. So it's a great practice exercise to be able to do the reverse and able to draw those. So here we go. The first one is acceleration time. Second one, velocity time. And the last one is displacement time. Awesome. Previous problem, we said it started off with this positive acceleration, so it's gaining speed. Constant positive acceleration. Then in the middle for a little bit of time, for 10 seconds, it told us that it was moving at a constant speed, so that means there is 0 acceleration. That means you just draw it like this. 0 acceleration. And then when it is decelerating, that just means it has a negative acceleration. Doesn't matter where you draw them, you do not need to draw them to scale, you just need to make sure this is positive, 0, and negative. All right, for your velocity time graph, we know in the middle, so let's say this middle section here, it was moving at a constant speed, so a constant velocity, positive velocity, like so. So we can start with that. We knew it started at rest, so velocity is 0. And then at some time later, it also came to rest at the whatever floor it went to. So what did it do to get from here to here? It increased its speed. It accelerated. Cool, we already showed that there. What about here is decelerating. It was decreasing its speed from this constant speed going back to 0. Beautiful. That's all you need to draw there. Now we need to do our displacement time graph. In order to do that, we know in the middle again, it was increasing its distance at a constant rate. So I can draw a line like that again. However, in order to show the acceleration, a positive acceleration here and a negative acceleration there, we need to draw some type of curve. So here it started at 0, and it increased. It's my exaggerated curve. It's increasing its speed. It's accelerating. Here, in order to show it's decelerating, it's going to be going at a certain speed, and then eventually it's going to flatten out and then stop at a certain, 12th floor, wherever it got to. So here, I don't know if you can see that, it's curved. Here is curved as well. Cool. All right, that's all you need to do. So on the AP test, I imagine they might give you like these 3 graphs, and they would say something like, describe what is happening. What could be a situation that would explain these graphs? So that's all you need to do for now. But now you know how to draw the graphs. Cool. All right, here's FRQ number 4. Okay, FRQ number 4. Again, you need to write a coherent paragraph. Lots of writing this week because the actual AP test is going to be lots of writing because that's happening. We're practicing a lot, and I look forward to seeing your explanations and talking about them then next week. So here we go. You have 2 cars. I need to pull up my picture. Okay, cool. So they're both going like this. They're both moving straight. They're right next to each other. This is car A. This is car B. They move like this. This guy moves here. This guy moves here. We'll say that. Okay, and it's going to say, the question says, which one do you think is more likely to lose control when they're going around the turn? So both cars are identical. They're going the same speed, and then they both make these respective turns. I will tell you, it's more likely to lose control if you have a greater external force. Remember when you're writing this paragraph, again, push you to look at that student exemplar, but remember your A, B, C, Ds. A, answer the question. B, what is the basic physics? C, cite numbers, either if you have like a data set, or cite the picture and then draw it all together. So for this, we're going to say you are going to lose control if the car a greater external net force. Cool. Let's just say greater net force. If you look here, this object is going around a circle. It's following the path of a circle. It's not going around the entire circle, but that's the motion that it's following. So we know a net force when an object is moving in a circle is centripetal force. This would be your basic physics for B. Centripetal force is equal to mv squared over r. So they're both going the same velocities, so we're going to keep that at 1. They both have the same masses, so that's 1 as well. So then this becomes centripetal force is equal to 1 over r. The reason why I kept r in there is that that is a radius. So let's say this here is the radius of this circle for car A. This here is the radius for car B. I see that car A has a much larger radius than car B. So you could say citing, this would be your basic physics. Citing could be A has larger radius and B smaller radius. All right, looking at this fraction here, if you put a larger number in here, so sometimes it's hard to conceptualize this, so let's put in actual numbers. So let's say A has a larger radius, let's say this is 4, and here let's say that's 2. Numbers, you can make them up just to show that comparison. So here, centripetal force would be 1/4. Centripetal force here would be 1/2. 1/2 is much larger. So smaller radius, larger centripetal force, more likely to lose control. So B, I don't know if you are a driver or experienced going around circles or sharp turns like this. I do not recommend practicing this at home, but it is much harder to go around a shorter curve like that with a smaller radius. Cool. That's it for part A. Your answer, I don't know if you got that, would be part B, more likely to lose control. It has a larger centripetal force and a smaller radius. Awesome. Part B, it's asking you to compare fabric seats to leather seats. I know leather is very smooth. Fabric is more rough. If it's rougher, that means it has a higher coefficient of friction. If it is smoother, that means it has a lower coefficient of friction. Our equation, coefficient of friction, is equal to force of friction divided by force normal. So it's asking you about the frictional force here. Which one's going to be bigger? If you have fabric seats or leather seats, assuming that the person doing this comparison is the same mass. So if you have a larger number here, you're going to have much larger frictional force. If you have a smaller number here, like a leather seat, your frictional force will be much smaller. So your A, B, C, Ds. I want to ask you specifically, greater amount of frictional force. Fabric seats. Basic physics is your equation. Cite them together. You could say something about rough and smooth and higher coefficient of friction and lower. So I'm going to say that is C. And then draw it all together. Again, there's a student exemplar links on Schoology. Maybe I'll put it in the link below. Anyways, yeah, that's it for our weekly FRQs. Thank you for joining in.